Okay, welcome to part two. So once I have my slope, I can use that slope with that point to create the equation of my right bisector in point slope form. Okay, so again, that's how I find one right bisector. You have to find all three. I'm gonna again let you do that on your own. Make sure you're okay with those, and check the push play and ready to see the answers together. Okay, so if you want to check your remaining bisectors here before you go too much further, so for the bisector of PQ, again, I found the midpoint of PQ and the slope of PQ. So my midpoint became 7 over 2, 1 over 2. My slope was 1, which means the negative reciprocal of that was negative 1. So I got the equation y equals negative bracket x minus 7 over 2 plus 1 over 2. For PR, same thing. Midpoint of PR was 5, 1. Slope of PR was 4 over 2, which is 2. Negative reciprocal for the perpendicular slope was negative 1 over 2. So I got my third equation down here. So now I have the equations for all three right bisectors. You'll see on my diagram here they all intersect at a point that I'm going to call A. I want to find that point of intersection. So again, pick any two of the equations you like, whichever ones you think will be easiest to work with, and solve for the point of intersection of those, and then check it in the third equation. Me personally, I mean, they all look relatively equal in terms of complexity. I'm just going to choose to work with the first two right here, the red one and the green one, when I do my point of intersection. You can choose something different if you like, but I'm going to work with the red and green one to find the POI. Give that a try and push play and ready to see the answer. Okay, so I took my two equations here. Again, they're set up nicely for substitution because they both already have y isolated for them. So I took my y equals negative 3 bracket x minus 5 over 2 minus 3 over 2. And since that was equal to y, I replaced the y in the other equation with it. So now I have an equation here, although it looks kind of ugly. There's only one variable in it, there's just x. So I just had to take some time, work through the algebra, expand, simplify, collect your like terms, and then eventually solve for x. So when I expanded through, I wound up eventually with negative 3x plus 6 equals negative x plus 4. When I solved that one, collected all my x's on one side, all my constants on the other side, I got x equals 1. At this point now, once I have x, I use one of the original equations to solve for y. I chose to use equation 2, but equation 1 would have worked as well. Put x equals 1 inside that equation, solve for y, get y equals 3, which gives me a point of intersection of 1, 3. Last thing, again, just like with the previous example, because there's three equations I want to see if they all intersect at the same point, instead of solving another system, I just checked to make sure that this point of intersection is on the third line. So I took my third equation here, set up a left side equals right side, put in 1 for x, 3 for y, and you can see that I get left side equals right side, and I work through the math. So again, that shows that all three of these right bisectors up here in this graph intersect around the point 1, 3. I know that doesn't seem to fit my scale on here, but it was just a nice, it was just a little rough sketch, right? So it might not be exact, but clearly the math showed me that it satisfied all three equations, so it is the point of intersection. So, and again, just like with medians, it will be the case where all three right bisectors will have a common point of intersection. Okay, in this case it's 1, 3, and that point of intersection is called the circumcenter. So the place where the three right bisectors or perpendicular bisectors intersect is called the circumcenter. What it means is that is the one point that is the same distance to all three vertexes or vertices or corners in the triangle. Okay, so let's take a look at a picture here. Okay, so here I have a triangle, and again you can see I've drawn this applet here has drawn the three right bisectors, and you can see they all have a point of intersection. No matter what I do with the vertices here, they all still will have a common point of intersection. And again, what's nice about this point, the significance of it, is that this point right here, it's the same distance to corner A, corner B, and corner C. So if you were to take out a ruler and measure that, you'd see it would be the same. And that'll be true no matter where that point of intersection is. Now you'll notice here there's some circumstances, like the one we just did also, where the circumcenter is actually outside the triangle, which might seem a bit counterintuitive, but again, you're looking for the point that's the same distance from all three corners. Sometimes that won't necessarily be inside the triangle, depending how those vertices are oriented with each other. So you look at this example right here. Here's our circumcenter down here, but you'll see that it's going to be the same distance if you take out a ruler and measure to all three corners, A, B, and C. Okay, so just to make a note of that, the circumcenter can sometimes be outside of the triangle. Again, the important thing is the same distance to all three vertices. Okay, that's it, that's all. So it's a little bit of practice there. Finding the centroid and circumcenter can take a little while, but it's a good process to know how to do. It's a good problem-solving type thing. And again, you know, there are some circumstances where the circumcenter and centroid may be useful, but it's good practice to be able to find them. Okay, that's it.